The story of the Wendelstein 7X is one of patience, persistence, and precision engineering. Conceived in the 1980s and developed across 4 decades, it stands today as the most advanced stellarator ever built. While most of the world fixates on ITER, the enormous tokamak being assembled in southern France, Germany's 7X quietly challenges its rival with a design that could change everything about how we think of fusion energy. Planning for the project began in the early 1980s, during a time when fusion research was losing public interest. Yet in August 1990, the proposal was officially submitted to the European Union. What followed was a 6-year bureaucratic marathon of assessments and revisions, which concluded on March 11, 1996. From there, construction and refinement stretched nearly 2 decades. 19 years later, on December 10, 2015, the 7X finally produced its first helium plasma, a moment that marked the rebirth of stellarator research. By comparison, ITER's first plasma test is scheduled for 2025. The current cost estimate sits around $22 billion, but projections suggest the total may exceed $80 billion by 2040. The 7X, on the other hand, costs roughly $1.1 billion. Even if that number were off by a factor of 10, it would still represent a far more efficient investment. Its advantage isn't just the lower price, it's what that money achieves. The Wendelstein design solves one of fusion's oldest challenges: the stability of plasma within a magnetic field. To understand why that matters, one must examine the twin problems that fusion scientists face: heat transfer and magnetic confinement. At its core, a fusion reactor is a glorified pressure cooker powered by atomic collisions. Like a fission reactor, it uses heat to produce steam and drive turbines, but the underlying physics are far cleaner and far more powerful. Fusion reactions release several times more energy than fission. They cannot run away into meltdown, and they produce only short-lived radioactive waste. The process begins by heating light atoms, usually isotopes of hydrogen such as deuterium and tritium, to around 20 keV, equivalent to over 200 million degrees Celsius. When these atoms fuse, they release about 20 million electron volts of energy per reaction. A fast neutron carrying 14 MeV leaves the plasma and slams into a blanket surrounding the chamber. That blanket transfers heat to a coolant, often helium or water, which can then be used to generate electricity. This is where the first major difficulty appears. The reactor must transfer tremendous heat while keeping the surrounding structure cool. The inner walls, separated from the plasma by mere centimeters, face temperatures greater than those at the surface of the sun. Graphite components can help handle the load, but if they degrade, carbon impurities contaminate the plasma and choke the reaction. Inside the 7X, engineers work to perfect this delicate balance, creating materials and cooling systems capable of running continuously for tens of minutes, an eternity in fusion experiments. But the bigger challenge is confinement, keeping the plasma stable long enough for atoms to collide and fuse. In a tokamak, this is achieved using a toroidal chamber, essentially a donut-shaped magnetic bottle. Coils surrounding the chamber create a magnetic field that loops the plasma in circles. Yet the magnetic field in such a torus is stronger on the inner curve and weaker on the outer curve, pushing particles toward instability. To correct this, tokamaks induce a secondary electric current within the plasma using a central transformer. This internal current twists the plasma and improves balance, but it also introduces new problems. First, that current can create violent instabilities called disruptions, where the plasma suddenly collapses, releasing huge bursts of energy that can damage the reactor walls. Second, the need for a transformer means tokamaks can only operate in pulses rather than steady state. Third, the complex magnetic structure demands enormous quantities of superconducting cable. ITER alone will use about 100,000 kilometers of niobium tin and niobium titanium wiring. And finally, even in perfect conditions, particles still drift away from their intended orbits. Those losses mean lower reaction rates and wasted fuel. To counter this, designers build bigger machines and stronger fields, chasing diminishing returns. That's why ITER is the size of a 12-story building, and why its cost continues to soar. The Wendelstein 7X, however, takes a sleeker approach. Its lineage dates back to American astrophysicist Lyman Spitzer Jr., who in the early 1950s sought to fix the very same drift problem. His insight was deceptively simple. If a plasma's path could be twisted as it looped around the torus, the drifts would cancel out. He built the first stellarator, named after the stars, at Princeton in 1951. Early prototypes twisted the plasma path into a figure 8, and though they only reached 500,000 Kelvin, the concept proved sound. Spitzer later realized he didn't need to physically twist the chamber. Instead, he could create a helical magnetic field using external coils wound in alternating directions. That insight birthed the classical stellarator. Unfortunately, the magnetic calculations required were far too complex for mid-century mathematics. Tokamaks, simpler and easier to control, took over the field. For decades, stellarators were treated as dead ends. Then came the era of supercomputers. With modern numerical models, physicists could simulate plasma behavior in detail impossible before. In the 1990s, German scientists used these tools to redesign Spitzer's dream into a perfectly optimized magnetic geometry. The result was Wendelstein 7X, a 5-fold symmetric stellarator whose twisted coils shape magnetic field lines into closed, stable surfaces that cradle the plasma like invisible glass. Each of its 50 non-planar superconducting coils had to be manufactured with millimeter precision. Together they form a magnetic cage so finely tuned that a particle could orbit inside for tens of seconds without touching the walls. Because the 7X requires no transformer, its magnetic fields are steady and continuous. This allows operation in a true steady state, free from current-driven instabilities. While ITER must achieve fields of 13 Tesla to reach break-even, the W7X is expected to manage with roughly 3 Tesla. Its total wiring length is a few hundred kilometers instead of 100,000. Construction times shrink accordingly. ITER's coil production alone took nearly 8 years. Despite its smaller field strength, the 7X achieves superior confinement. The plasma remains stable, disruptions are virtually non-existent, and the machine can run longer shots, limited only by heat extraction. Another advantage lies in its scalability. Stellarators can achieve stronger confinement without having to grow much larger, since their field geometry handles plasma drift naturally. That makes them attractive for future reactors aiming for continuous power generation rather than pulsed experiments. Still, challenges remain. The complexity of the magnetic coils makes construction difficult and expensive. Even small alignment errors can degrade performance, yet the results so far are promising. Since 2015, every testing phase has met or exceeded expectations. The current upgrade, installation of an actively cooled carbon fiber diverter, aims to let the machine sustain plasmas for up to 30 minutes. If successful, Wendelstein 7X will demonstrate that a stellarator can operate continuously, a crucial step toward a true power plant. The implications are enormous. If a future reactor can combine W7X's stability with slightly higher confinement efficiency, humanity could finally have a practical path to limitless, clean energy. No greenhouse gases, no long-lived waste, no risk of meltdown, just the same process that powers the sun, tamed within magnetic coils. Looking ahead, researchers already discuss a next-generation stellarator using quasi-symmetric 4-fold geometry. Such a design could eliminate residual magnetic harmonics, flatten curvature, and further improve particle confinement. Each step takes the concept closer to break-even, the moment when a reactor produces as much energy as it consumes. So far, the 7X has shown that steady-state operation is achievable, and that its engineering tolerances are reproducible. If the final phase succeeds, it will prove that fusion doesn't have to rely on colossal tokamaks. For the first time in decades, the field has 2 viable contenders, one driven by brute force, the other by elegance. The future of fusion may not be decided in a massive reactor in France, but in a twisting magnetic labyrinth deep in northern Germany. And if Wendelstein 7X continues to perform as it has, ITER may not look nearly as impressive when the dust settles. That's the quiet revolution happening behind the scenes, a machine that bends both magnets and expectations. And with that, the story of Wendelstein 7X continues. The next tests will tell whether this beautifully twisted design truly holds the key to our energy future.